Thank you very much. Hello, everyone. So I'd like to start off by maybe talking a little bit about what astrophysics is, because you're all here for that. What is astrophysics? What does an astrophysicist do? How do I think about what my job is? Okay. To start off with, astrophysics is a kind of physics. Astro means a star in Greek. So it's a kind of physics, which is a kind of science. And I don't know about you, but even though grade school was a blur, I kind of, every year I sort of remember them dishing out this new textbook about, science every grade level, and it was always some different kind of science. It was biology, or it was earth science, or physical science, or whatever. But it didn't really matter what it was, because every year the first chapter would always be like, what is the scientific method? It was always the same exact chapter, and they always had some diagram like this that explained the same old steps that which were basically like, okay, I pick my field of study, I come up with some hypothesis, I do an experiment, I do, design this experiment really well, I do the experiment, I gather the data, I process the data, I analyze it, and I tell my friends and all of that. And we rinse and repeat. Okay, and so when I think about, when I ask my subconscious, like, what is a scientist, what is like the stereotypical scientist, I kind of think of like a chemist or something, right? And so the chemist thinks like, okay, well, what happens if I do some experiment, right? And they may have a hypothesis for what they think is going to happen. The chemist can go into the laboratory and they can actually do this experiment. And, then they get some result, and the result is either right or it's maybe not so right. But that's science. That's like kind of the stereotypical kind of science that I think about. And we astrophysicists, in a way, we are scientists. We are scientists, I hope. All right, but there are fundamental differences, and I'd like to talk about that a little bit. So here's a picture of an astrophysicist I found online. Not really sure who it is. Cameron, do you know? Cameron is an astrophysicist, and astrophysicists, we ask very similar questions to chemists. But instead of asking, like, what happens if we mix an acid and base, we might ask a different sort of question, like, what happens if you put that much hydrogen all in one place? That's 4 with 30 zeros after it. So we would call that 4 times 10 to the 30. But I don't know if everyone knows what that means, so we'll just have this. But you can't, it's too expensive, too hard to get that much hydrogen, so you can never really do that experiment. And so the way I like to think about the job of an astrophysicist is like, imagine there is a lab, but the lab is off limits. Like, it's so expensive, all the chemicals are so expensive that you're not allowed to touch them. You're only allowed to look through the window, while the owner of a lab does the experiments. And the owner of the lab is an adult, aggressive, male silverback gorilla who thinks that he knows how to do science, but he has no idea, so he's just sort of like knocking things off of shelves, things are shattering, glass is shattering, things are changing color, things are setting on fire, things are blowing up, and Cameron just looks through the window and he watches in horror as this happens. Look at all these chemicals that I can't play with. So, yeah. But then he sort of looks very closely, the gorilla's happy that he's, done science, and he leaves. And Cameron gets to look through the window. He doesn't even know what any of the chemicals are. He can't read the labels, all right? But he realizes that near the window there is this, what he figures out by looking is, 4 times 10 to the 30 pounds of hydrogen, right? And, somehow, even though he can't do this experiment himself, and even though nature basically isn't making this mess with him in mind, he's still able to answer this question. What happens if you have 4 times 10 to the 30 pounds of hydrogen? Well, you get something that looks like the sun. It's quite amazing that we can ask questions like this as human beings who can't do these experiments because nature creates those experiments, not because it wants us to know things. Actually, it's quite hard to extract this sort of information. We have to be a bit clever. But I sort of think about that as fundamentally why astrophysics, that's the unique challenge that we face. Another thing I'd like to say about astrophysics is like, most of what we learn about space, things in space, come from light. Now, not everything, right? We can send spacecraft to certain nearby objects. We can use gravitational waves, if you know what that is. We can detect neutrinos, but the vast, vast, vast majority is just us looking at stuff and being very, very creative with how we use light, right? So For example, we can look at how bright something is, we can also look at its color, we can look at a specific frequency range. Maybe we look in the radio, maybe we look in the infrared, the optical, the visible light. For example, maybe the gamma rays. Maybe we look at polarization. We can be all sorts of creative, right? And so most of what you've heard about astronomy is just us looking at stuff and being very clever about that. And that's all well and good. I feel like it's fun. It's like a puzzle, trying to extract this information. But in another way, this is like a very fundamental limitation, because if you're like me and you care about stars, then this is a real challenge. Because if the information is coming to you from light, that means that you can only directly ever measure something if it's separated from you by transparent stuff, transparent to light. Right? So I can look at the surface of a star because what's in between me and the star is just this transparent nothing, a vacuum. But I can't see inside of a star because it doesn't really matter what color I go to. The star is opaque. I'll never be able to see through it with any color. And so, I feel kind of bad because as, a stellar theorist, I want to make a model of a star, how the star works. But if I only have information about the surface, maybe I can do certain things, but then there are certain things I might never know. Okay. Oops, that's not the right, yeah, so it's all surface level, sad face. But, one thing which I'd like to say is that when you're an astrophysicist, when you talk to people, they sort of think like what you do is quite lofty, you need to know a lot of math, and like the intuition is very difficult, but in contrary, I would say that as an astrophysicist, I try to adopt as much intuition from my everyday life and put it into my studies, because it turns out that even if you have a person which is 50 kilograms, or you have the sun which is 2 times 10 to the 30 kilograms, it's all made of stuff, and so in many ways the intuition for understanding it is very similar, and we can use analogies to see if we can be cleverer about how we extract information from something like a star. So let's just forget about, let's pretend that we're not talking about astrophysics right now, and let's just say that instead of being an astrophysicist, Cameron here is a bell enthusiast. So he's just looking at a bell far away, he's not allowed to walk closer to it, he just sees this bell. So he sees it and he's like, okay, I kind of know like what color the bell is, so maybe I can guess like what the surface is made of, and he can tell that it's bell-shaped if he looks really closely, but there are some things he's not going to know, like he can't see inside the bell. Right? So this sounds very similar to the kind of problem that I've just been talking about. But if somebody rings the bell, then suddenly he can learn something else. Like, from intuition, from everyday life, if I took a bell, but I just like made it completely solid, full of iron, it would just sound like a thump, right? If I hit it. Whereas if it were empty, it would sound, like a bell, right? And like whether the bell is like a crap bell or not, doesn't depend, it might be sort of something very orthogonal to like what you can just see. Like if you just look at a bell, you may not know this information. And the idea here is that even though what you're actually observing is just sound waves excited off the surface of the bell, somehow the notes that the bell rings at depend a lot on the interior structure of the bell, not just the surface of the bell. So we can basically translate that information, that idea one-to-one to stars, and talk about starquakes, which are just oscillating stars. So if you just look at the sun, you can tell that this is a star that's yellow and it's spherical, but you don't really know that much else. Maybe you know some physics, so you can guess. But only with information from starquakes, watching starquakes happen, watching the brightness of the star change, because of something driving it, can you understand something like the center of the sun actually rotates a bit faster than the surface, right? Which is something that we just can't see. And so the way that I like to think about that is that when you rely on an oscillation, you're basically using the fact that even though a star is opaque to something like light, it could potentially be transparent to something like a sound wave. All right, so you allow the sound waves to bring some of the information out of the core of the star, put it on the surface, and then light does the rest, and it brings us that information all the way over here. Okay, so I've talked a lot about like, okay, well, we should listen to stars, but what does a star actually sound like? What does that even mean? Well, you watch a star, basically, you can watch its brightness change over time, just like you can listen to like the sound waves that come off of a bell. And then you can basically plot, on this sort of plot, the up and down axis, or the y-axis is basically how much energy is in a note, essentially. And then on the left and right direction, that's going to be like basically the frequency of that oscillation, or what I put here is the period. So basically like how long does it take that oscillation to go back to where it started, and I put it in here in minutes, and this is what the sun's oscillation power spectrum looks like, right? And so you can notice a few features. So first of all, it sort of looks like a kind of bump, where there's a rough bump around 5 minutes, these 5-minute solar-like oscillations in our sun. And then also, if you look really closely, I'm not sure if everyone can see this, it's basically like a fine-toothed comb of like peaks or groupings of peaks that are basically evenly separated in frequency. So it's like a comb. Oops. Yeah. And so that's all well and good. So, maybe we don't understand why the spectrum exactly looks like this. But we can go and look at another star and see if we can try and understand why this happens, or try and learn a bit more about stars. So we can think about a different kind of star called a red giant. So that's the kind of star that like Aldebaran is. This one is called KIC phone number. You can ignore that like random bump on the left. This is basically the same plot, but for a red giant star. It's a red giant star that it's not in our solar system, so we basically can't take a real picture of it. We only see the point of red light. That's all we see. We just document how much that brightness changes over time. And we get a spectrum that looks like this, right? Which is very, very similar. It's basically peaked at some frequency, and then also it's roughly it's roughly an even frequency space cone. It's a little hard to see there, but you can kind of squint and maybe guess that that's the physics is the same. And as if maybe if you don't look at stars a lot, this is not that surprising. They're both stars, they're both very similar objects, but I just want to communicate to you how vastly different these two kinds of stars are. So maybe I should explain what a red giant is. So here's the sun. This is all not going to be to scale, but to try and get a sense of scale, I'm going to say pretend that the sun is the size of a marble, right? So the sun is what's called a main sequence star. It burns hydrogen, and that's why that supplies the energy to keep it from collapsing. And then at some point, the hydrogen runs out, and you end up with some helium in the core, and then that core can't burn anymore. So you end up burning hydrogen around it, and the sun in 5 billion years will eventually expand into a red giant, and it will basically accumulate these helium ashes in its core until the star kind of expands. And it will keep expanding until it is roughly 200 solar radii across. So if the sun is a marble, then eventually when it's a red giant, it will keep growing until it is about the size of a car, this one, right? And that's where half of the mass is, in this big fluffy envelope, which is super low density. And then the other half of the sun's mass, which was in this marble, is now in a small ball, which is roughly the size of a human hair, which is pretty insane, right? So, the sun is this pretty homogeneous object, sort of, in density, whereas the red giant is basically like this super extreme stratified object with like a vast range of densities in it. So it's really weird that when you ring them, they look very similar. But we can try and see if we understand why maybe there are some similarities there. And so first we can ask what rings the star? Because, something needs to ring the star, something needs to ring the bell, otherwise you can't hear it and you won't learn anything about it. It turns out in the sun, the outer layers are what's called a convective zone. This is real data, this is a real movie, this is not a simulation, which is pretty insane. And I've put over here a picture of the United States, roughly speaking, and you can see that each of these, what are called convective cells, is roughly the size of Texas. The surface of the star and the outer layers are basically like a boiling pot, where there's energy being added to the bottom, and then these blobs move up and down, right? And that constantly and randomly drives the oscillations in the star, and so we kind of always see it sort of randomly oscillating, but in a way where you can extract the notes that it rings at. And unfortunately, we don't have quite as good of a movie like this for something like a red giant, but we can do simulations, and there's this simulation by a grad student at Max Planck Institute of Astrophysics, of a red giant. You can see that this is the entire red giant. This is not a zoom in of the surface. And on the top right, I've shown the size of the distance between the Earth and the sun. So that's basically the Earth's orbit. So these stars are quite massive. In fact, I tried putting the sun on this scale, and it's basically 1 pixel wide. And also, the nature of that convection is quite different. These blobs are basically half the size of the entire star, the entire star's size, right? They're not a tiny fraction of the size of the star. A blob the size of Texas is going to be much smaller than the surface of the sun, even though we think it's large. Whereas on a star like Betelgeuse, for example, which is a red supergiant, the blobs are very, very large. But even though they're different, it doesn't really so much matter. Like the reason why these two stars ring is more or less the same. And it turns out, it's kind of hard to see in this movie, but it turns out that red giants actually oscillate a lot slower because these blobs move a lot slower. So I don't know if I didn't really point this out before. If I compare the power spectra, you can see the difference in units. The sun oscillates on a scale of minutes, whereas that red giant oscillates on a scale of hours, and some can oscillate even slower than that. And it turns out that the distance, the sort of fineness of the cone, the distance between the frequency peaks, is also different between these stars. They turn out to be a lot closer in red giants. That turns out to be kind of related to why like a big instrument like a classical bass is going to be lower than something like a violin. It's just because like bigger things tend to ring at lower frequencies. But in any case, that's really, really neat because once you know the physics there, once you understand these like rough reasons why the peaks are where they are and what drives the oscillations, you can start to do things like extract the masses and radii of these stars. Again, when you look at something like a red giant, you only see a red dot. You can't even make out its size. You can't even like do what you would do with a bell where you can see its shape. You can't do any of that. But somehow you can still understand, you can weigh the star, and you can also measure the radius of the star without even making it out, which I find to be insane. And so far we basically talked about normal sound waves, like pressure waves, right? So that's basically the kind of wave that's delivering information from my mouth to your ears. This is due to like the restored force caused by like the fact that air doesn't like to be compressed, so it pushes back. This is just an example of a sonic boom. That shock front basically propagates at the speed of sound. But there is a different kind of wave that we're used to in our everyday lives, and we can kind of guess like, okay, this kind of thing probably happens to stars as well. And you can do some math and you can be sure about that. Which are called gravity waves. They're not gravitational waves, so they get mixed up a lot. But basically, these are things like ocean waves. So like instead of being restored by the the compression of something like air pushing back, it's instead restored by buoyancy. So it's more like akin to sticking a rubber duck on the ocean and then have it like sort of rock back up and down. It's not because you're squeezing the air particularly hard, is rather because when you push the rubber duck down, the water is like, hey, I'm heavier, I deserve to be below, and then it just sort of pushes the rubber duck back up as it tries to get underneath. And so that's what's going on the left, and then on the right, I think is a really fun example. This is a phenomenon called a lenticular cloud. This is basically what happens when some air flows over a mountain, and then that excites some what are called internal gravity waves. And that produces these weird looking like pancake-shaped clouds. I just want you to think, use your everyday intuition. You probably, can, think about this a bit, and you realize that, well, pressure waves, they're like fast things, right? Like I think my mile time, I do run, but my mile time is pretty bad, and some people might have pretty good mile times, but I don't think anyone's mile time is 5 seconds. But that is the speed of sound, 300 meters per second. And it's so fast, of course, that like, when you look at me speaking, you basically see my mouth move, and then instantaneously you hear the sound. You don't even register that they're, disconnected things. Whereas with something like an ocean wave, you can watch that happen. You can watch this propagate. It's a slow process. Right? Gravity waves are slow. However, it turns out that, as I mentioned before, red giants, they have cores which are super, super, super dense, and that means that the gravity waves in the core end up being sometimes roughly the same frequency as pressure waves in the envelope, which means that sometimes the waves in the envelope actually talk to the waves in the core, because even though we think of gravity waves as super slow, actually the gravity waves in the core are quite fast. So they sort of link together, and when that happens and we understand that, then we can also gain information not just about the bulk properties of the star, like its radius and its mass, but also things about the deep interior of the core, which is insane. And so I think, in the last few minutes, I'd just like to sort of make this point. Like, if you look at a star, you gather the light, then you can't really distinguish these three stars A, B, and C, like a game show, right? And if you have pressure waves, that's great. You can measure the masses and radii of these stars. That's certainly something you can't tell just by looking at it. But, you actually can't really tell these stars apart super well either. But then if I add gravity waves to the mix, then you can see that their cores are going to be quite different. And I'm not going to go into exactly how that modifies the oscillations, but they do in some way that we can do some math and understand. Oops. So the first type is just a normal red giant branch star, like the kind that I described. So here's me explaining it 5 minutes ago. And that's basically like a situation where you have like an Earth-sized ball of very, very compact, what we call degenerate helium. That's basically the case that I explained before. That's what our sun is eventually going to become. The second kind of star has a lot puffier of a core. The core is actually still pretty small. It's about a Jupiter radius, so much smaller than the sun still. About the 10th of the radius of the sun. But okay, like quite a bit larger than the Earth. And this is the kind of star which descends from like a star which would be 2 solar masses or so. So that's quite a bit larger than our sun. And then also the one on the right is going to be what happens when you go all the way through this whole process. You know, your star runs out of hydrogen, it goes all the way up the red giant branch, it becomes the size of a car on the scale, and then shrinks back down very quickly to the size of about a deck of cards on the scale, or about 10 solar radii across, when it starts to ignite its helium. Now all 3 of these stars, they look identical, basically, but if you look at their oscillation spectra, you can pretty quickly distinguish them. And I had some more stuff that I wanted to say, which is, kind of about how you can use this technique to do other things. Like you can, figure out when stars are unusual. Sometimes stars, don't really comport to your expectations. For example, there are certain stars that have the structure of star A, but the mass of star B. There are some stars that have a planet very close to a star like star C, even though they should have engulfed everything around them. There are a lot of fun games that you can play when you're in a field like astroseismology and you have this cheat code where you can look inside of stars. So basically, when you have access to something like this, when you can see past the surface, then you can do a little bit better sleuthing. And maybe what I hope that I've convinced you is that, while we astrophysicists really like to look at stuff, like we like to look through telescopes at stars, we like to look at things, sometimes it helps to listen. Oops. Thank you. Yeah, anyone have any questions? Yeah.
If you were to rescale the power spectrum to hertz within a hearing range, what would the sun sound like?
Oh yeah, okay. So the question was basically if I were to rescale the sounds, like